My name is Jack Van Lightly. I'm a principal software engineer at Splunk, and I have my colleague here.
Hi, I'm Ivan Kelly, also at Splunk.
And what Ivan Kelly won't say is he's one of the main engineers behind Pulsar, and BookKeeper has been involved for years. So, whereas I am relatively new and just joined. So, performance. A lot of performance is about scaling out or scaling up. And the good news is that Pulsar and BookKeeper, the storage layer, can both scale out and up really well. And we can scale out and up in different ways. So one of the main ways of scaling out is that we can have different cluster sizes. So we could have a small cluster of 3 Pulsar brokers and maybe 4 BookKeeper nodes, which do all the storage, or we can go bigger and bigger and bigger until you get to large clusters like we have at Splunk, where we have maybe a couple of hundred Pulsar brokers and even more bookies. But it's not the only thing we might want to scale out. We might want to send a lot of data down a single topic. So when we've got a relatively low or medium load on a topic, just a single topic partition is enough. But as we get more traffic through a topic and more clients connected, we might want to shard a topic out into multiple partitions and grow and grow and grow. And at Splunk, we even have topics which are composed of 1,000 partitions. We can also scale up, so we can have our BookKeeper nodes, on small servers with just, a couple of gigs of RAM and a small disk. But when we want to start pushing a bit more data through them, we need to scale up, give it more CPU, more memory. We're going to want to separate our journal from our ledger data, so 2 different workloads are separated. And then we can even assign more and more and more disks and more and more and more CPU and memory. But all this does cost money. Nothing is for free. We have to pay for our CPUs, our memory, not only the disk size, but what throughput it's capable of. There's also the network. If we're in the cloud, we have to pay for data crossing availability zones. So what can we do? Compression is one of the first things we look to reduce network utilization and reduce disk utilization and space. We can also look at maybe reducing our replication factor. Pulsar does offer some safety and availability when running at a rep factor of 2, which we'll look at a little bit later. Many other messaging systems will need a minimum of 3 for high availability. But there's some trade-off of safety versus cost there. But can we do more? Is there anything else we can do to reduce the cost of ownership? Now that we know we can scale out, how can we reduce cost? So in this talk, we're going to be talking a lot about the BookKeeper journal and how it comes into the equation. So first of all, let's just have a look at what the journal is. So a journal is also known as a write-ahead log. It's common in data systems, think databases. So databases offer ACID guarantees, and usually the journal is responsible for things like atomicity and durability. BookKeeper also has a journal, and it also uses it for strong durability, but it also uses it to help sidestep some performance issues. And that's what we're going to look at. But first, let's take a little step back and look at how Pulsar topics are stored. So each topic partition is actually a segmented log. It's not a monolithic log, say like in Kafka, where the entire log has to fit on a single server. It is actually split up into segments, and these segments are called ledgers. And that is BookKeeper, and that's where BookKeeper comes in. And each ledger can be stored on different sets of nodes. So we can have many, many BookKeeper nodes, and each ledger can be stored on a different set of nodes. And then the entries in those ledgers are written to entry log files on BookKeeper. And also there's metadata about entries and ledgers stored in an index, which is RocksDB. So why have a journal? If we're writing the data to entry log files, why do we need a journal? Well, we could say, let's just have one entry log file per ledger. And that's kind of similar to, say, how Kafka would work, where you're writing to one file per topic at a time. But the trouble is with this is that it's okay when you've got a few ledgers, or if you've got SSDs, maybe you've got 50 ledgers or more, then we're okay. But what about if we've got 1,000 ledgers being written to at the same time, or 10,000? That's when we get a lot of random I/O and things start to break down. So another strategy we could go for is, well, actually, let's just write to one entry log file at a time, and we'll get nice sequential writes. We'll interleave our ledgers and the entries of those ledgers in the same entry log file. In the index, we'll know where to go to look for that data. But the problem now is that we have random I/O in our reads. The reads are having to jump around all over the place. Nothing is contiguous. So there's something we can do. We could not necessarily write as things are coming in. We can buffer in memory our writes and then do a sort operation and then do batch writes. And that way we get sequential I/O both on the writes and the reads, but we also pay a price. And that price is write latency, because BookKeeper has always cared about data safety, and it will not, by default, acknowledge a write until it's been f-synced to disk. And so if we're going to wait for this buffer and sort process before we f-sync, then write latency goes up too high. So this is where the journal comes in. We can kind of get the best of both worlds. So we write all data to the journal as it comes in, all the entries of different ledgers interleaved, and everything is sequential because it's just writes. We're not reading from the journal. And we get low latency because we can perform many, many syncs per second and have really low latency on the writes. Then all those operations go through the caches. On periodically, we're sorting the data that's not been written to disk, and we flush it, sort it, and sync it. And many of the reads that come through the various write and read caches, don't actually even have to hit disk at all because they're already in the caches. So that's one, the main reason why we've got the journal, but it does have some costs. We have the double write. So we're not just writing the data once, we're writing it 2 times. Also, there's the provisioning. Now we kind of want to have at least 2 disks, because when you share on the same disk, especially if it's a spinning disk, if you share the journal and the entry log data on the same disk, it can harm throughput. So now provisioning is a little bit more complex. So also we've got Iops, right? So Iops in the cloud are expensive. We have to double the amount, and yes, we can end up with the same performance as if we didn't have the journal at all. Like, let's just say we ran without the journal at all, just turned it off, but we're having to pay double the price for all those writes. But could we turn it off? What could go wrong? Let's look at Kafka as an example. So Kafka writes all its entries to the page cache, which is basically in memory, and then the operating system is syncing that to disk. So if a Kafka server were to lose power or die abruptly for some reason, then that server, anything that wasn't flushed to disk, is lost. But as long as at least one copy of each confirmed message exists, Kafka will recover and everything will be okay. So can we do the same with BookKeeper? Could we just turn it off, and will it all recover in the end? Well, let's just have a quick look at Kafka first. So let's just say we have here 3 brokers. Okay, we have some entries in each broker. Now the green ones, those have been synced to disk, and those yellow orange ones, those are only in the page cache, not been synced yet. What happens if broker 2 has a power outage? Well, when it comes back up, that data is gone. Okay, so it's lost the data it had only in the page cache. But that's fine, because broker 2 will then start fetching data from the leader, and one by one it will recover, and we'll be back to the full redundancy. But what if there's some kind of coordinated failure? Something like the whole data center goes out, and we don't have any availability zones or anything. Well, once they all come back online after the power loss event, we've now lost all the data that was in the page cache but not synced. And guess what? We just lost committed data. And we also did it silently. So system carries on. And unless you've got any special monitoring in place, you would never know that you've just lost data. Now, with Pulsar, this would not happen. And it's because of the BookKeeper journal. When BookKeeper says, hey, I've got the data, this sort of thing cannot happen because it's written to the journal and we're syncing to disk before we confirm. So Ivan's going to step in and he's going to have a look at what could possibly go wrong if we just turn the journal off with BookKeeper.
Okay. So first, a little bit of background info. So Pulsar is not like, Jack covered this briefly earlier, Pulsar is not like Kafka in how it stores its data. A topic in Kafka, or a partition, I'm just going to say topic as shorthand, is stored on a set of brokers, and that topic, storage of the topic is on the brokers, the serving of the topic is on the brokers, and it never moves. In Pulsar, we have the separation of the serving and the storage layer. So the serving layer is the brokers, and they get assigned topics, but that topic can move around between brokers. And the storage is on BookKeeper, and the topic itself, which is broken into smaller segments, we call them ledgers in the BookKeeper parlance. They can also move around. So, Jack, did you mute? Someone saying that it sounds very poor. Okay, I'll turn off the camera just in case. No, okay, Jack, you're not muted. There we go. Okay. So, because the ledger is broken into these segments have to roll every so often. So, if in the common case, the ledger is rolled every 10 minutes or every 10,000 entries, whichever is longer. But it can also roll in the case where a topic is being handed off between two brokers. So if broker A crashes, for example, broker B will have to take on the topic, recover the ledgers there, and start its own ledger. And then these ledgers are put together into a linked list, which is your topic. Now, the reason we need the journal is for correctness in this recover and close operation. So, Jack, if you could move to the next slide. So when we do a recovery, what we're basically trying to figure out is what is the last entry that in the ledger which has been acknowledged to the client. So if we acknowledge an entry to the client, that entry should never disappear. So the recovery process goes like this. Let's say we have, go back a slide. Yeah, let's say we have 3 bookies and a ledger, and 5 of the entries have made it to the first 2 bookies, and 2 of the entries have made it to like the 3rd bookie. When we run recovery, we will send a read request to each ACK quorum that's possible in the ensemble. So in this case, we have an ensemble that has size 3, write quorum 3, ACK quorum 2. So there's three possible ACK quorums. There's bookie 1, bookie 2, bookie 3, and bookie 3 and bookie 1. If we get responses from one bookie in each ACK quorum, we can proceed. And the reason we do this is that if we required that we hit all bookies, then we wouldn't be able to make progress in the case of a bookie being permanently down. So let's say we send a request to read the last committed entry to all bookies. Bookie 1 doesn't respond in a timely manner, so bookie 2 and bookie 3 respond. We will see that we have 5 entries in bookie 2, and at that point we will re-replicate all 5 entries to all 3 bookies, and we will close the bookie at entry ID 4. So entries start at 0, so it's like 0, 1, 2, 3, 4. And this is correct, and this is a recovered ledger, and we can make progress. So the decision table for deciding whether we can make progress is like this. So if we have, let's say we're reading entry X from a set of bookies B1, B2, and B3. If we receive OK from 2 of the bookies, then the entry definitely exists. If we receive no such entry from 2 of the bookies, so this overlaps each possible ACK quorum, so no entry, well, entry X has not hit enough nodes to have been positively acknowledged to the client. Likewise, if we get no such entry from 2 of the bookies and we just haven't got a response from 3rd bookie, we know that even if bookie 3 later comes back and responds OK for that entry has not hit enough bookies for it to be considered ACKed. Where it gets tricky is where we start having multiple entries, multiple errors. So in the case where we have 2 errors and 1 no such entry, it is possible that a entry X has been written to bookie 1 and bookie 3, has been acknowledged to the client, and so may exist. So we don't actually know in this case. And in this case, we cannot actually make progress. In the case where we get an error from bookie 1 and a no such entry from bookie 2, this means that we cannot make a decision based on this information. So we have to wait until we see the response from bookie 3, because bookie 1 could have received the entry and bookie 3 could have received the entry. So we cannot do anything with the information from B2. So what happens in the case where we don't have a journal, we're only buffering in memory, and bookie 2 crashes and we lose the data that was unflushed on bookie 2. So in this case, if we try and do a recovery, we'll send a read last entry for entry. Okay, so this is a little bit confusing since we're counting from 0, but we're reading entry 2. So entry 2 does not exist on bookie 3. Entry 2 does not exist on bookie 2 since it's lost all its data. If we, in the recovery protocol, we only need to read 1 bookie from each ACK quorum. So if we read from bookie 2 and from bookie 3, that satisfies that condition. So let's say bookie 1 times out, or it just takes a little bit longer. If we get the response from bookie 2 and bookie 3 first, we'll have satisfied that condition. We'll have seen that the last entry in the ledger is entry 1. So there's entry 0 and entry 1 on bookie 3. And at that point, we have lost data, because we will continue the protocol and we will close the ledger at entry 1. And this is silent data loss. So how do we get around this without a journal? We need to change the BookKeeper replication protocol. And for this, we have introduced a new concept called limbo. And limbo turns the no negative response into a, I don't know, go ask someone else response. And it works like this. So we have a unclean bit that we set in the ledger storage. And this bit gets set the minute you open the storage. So when you open the storage, you start writing stuff. You don't even need to start writing stuff, but you set this unclean bit, and then when you have a graceful shutdown, so let's say you're doing a rolling restart of all your bookies, you will flush all your data, and once you're sure that all your data has... So I'm just after seeing a message. Did we lose Ivan? Okay.
I can hear you. Don't worry. Carry on.
Yeah. Okay. No problem. Once you're sure that all your data has been flushed to disk, you clear the unclean bit and continue shutdown. Then on subsequent boots, if you detect the unclean bit has been set, so the unclean bit has to be persisted durably. If you detect that the unclean bit has been set, then you know that you have had an unclean shutdown. There may have been data in your buffers that never got flushed, so you have to take some remediation. And in this case, what we do is we go to Zookeeper, we find out which ledgers were actively writing to that bookie at that time. So these would be ledgers that are open in that they haven't been closed or sealed, and the bookie exists in their final ensemble. So for these bookies, for these ledgers, we need to mark them locally as in limbo. And once we mark them as in limbo, which also has to be a persistent operation, then we move on and the bookie can start serving all other requests as normal. Then, while these are in limbo, any request for to read entries that do not exist will, instead of getting a no such entry or no such ledger response, they'll get an unknown response. And this unknown response, to the client, this is equivalent to a timeout or an IO error. So it basically says to the client, this entry may have existed here at some time. I'm not giving it to you now. I don't know. And when the protocol, actually we'll go on to the next slide, when the recovery protocol sees this message, it will basically skip it, take it as a timeout. Sorry, Jack, could you go back one? Yeah, so there's also a background process that runs for ledgers that are in limbo. So once we mark them as in limbo, we know that we cannot serve them. But if they are in limbo, that means that like whoever has been writing to them hasn't detected that the bookie had failed, so it hasn't hasn't changed the ensemble to replace the bookie. If they haven't detected that it's failed, we may as well just try and close and recover that ledger as soon as possible, so that we can bring the data in that ledger up to the replication that we have specified. So in this case, we have a background process that scans the index to see which entries we should have. Which entries the bookie does have, compares that to what's in Zookeeper metadata, which is the ground truth for what it does have, and it starts pulling any entries that are missing. So next slide. So while the ledger is in limbo on the bookie, as I said, it will respond unknown to any read requests for entries that it does not have. And this fixes the recovery protocol for this case, so we don't lose data. We don't silently lose data. So let's take this case where bookie 2 has, go back. So bookie 2 has rebooted. It's found that it has lost the data, so it marks the ledger as in limbo. So we run the replication protocol, and we see that we get responses from bookie 2 and bookie 3. So bookie 3 says no such entry. Bookie 2 says unknown, which is equivalent to an error. So we cannot decide if entry 2 actually exists or not based on this information. So we have to wait on bookie 1, and in this case it times out and we cannot make progress. However, if bookie 1 actually responded, we would be able to make progress because we would have had non-error responses from 2 bookies in the 1 bookie in every act quorum in the ensemble. So next slide. So if it did respond, timeout is actually incorrect there, but if it did respond, we would be able to read forward and re-replicate everything that was on bookie 1 to bookie 2 and actually bookie 3 as well. So that slide's actually wrong.
Yeah,
and
sorry
then,
about that.
Yeah, no worries. And then close the ledger at entry number 4. And now I'm going to hand back to Jack. He's gonna, we've worked through this in TLA, and he's going to talk about those results now.
Okay, thanks, Ivan. So when I joined, Ivan had already worked out a lot of this, and one of the first things I did when I joined the team was to, as a way of learning Bookkeeper in detail, was to reverse engineer the protocol from the code.
Hi, Jack. I think you're muted. Can you turn on your mic now?
I'm on. Can you hear me?
Oh, I can hear you.
Yeah. Okay. So I modeled the Bookkeeper protocol, the replication protocol in TLA Plus, and so we already had that available. So all we had to do to get confidence in this kind of limbo status was to extend the specification to add arbitrary data loss and also limbo status. So just a quick thing about what TLA Plus is, because not everyone will necessarily know what it is. It's basically a way of modeling a system and verifying it to check for errors. So you can model anything from algorithms, concurrent systems, or distributed systems. And you model your system in terms of its actors and the interactions of the system. And then you can verify certain properties about it. So we split those properties into safety properties and liveness properties. So safety properties are typically invariants. So nothing bad will happen. So, no data is lost. Clients never get the wrong result. And then liveness is more about, well, something good eventually happens. So if we have, a leader election process, well, it will eventually complete. It cannot enter into some kind of cycle where it never escapes. Data eventually gets confirmed, that kind of thing. And then you can use model checkers, and they will explore all the combinations of the interactions between the actors in the system and various events. Like you can simulate crashes and restarts, and it will basically explore from millions to trillions of different combinations to find a way that your system could go wrong. And so what was nice is that once we'd modeled it and we didn't enable the limbo status, it straight away, within a minute and 16 seconds, was able to find the counterexample like we've already explained, like Ivan explained. And it matched kind of what we predicted perfectly. And it had to kind of explore, you see here, like 4 million different states, of which, million states were unique. And so then we enabled the limbo status in our specification and let it run, and we let it run and let it run, and days and days and gigabytes, terabytes of disk usage showed that it couldn't find a way that with the limbo status and the sort of self-repair that it could lose data. So that gave us a lot of confidence that the design was good. So there was also something I mentioned at the beginning of the talk where I said that Pulsar can go down to a replication factor of 2. And this can be a way that if you have got tight margins and you've got data that, the value of each item is not necessarily mission critical, then it's something you can do. So I like to joke that Bookkeeper and Pulsar are like Maltesers, and things like Kafka are like Toblerone. So Toblerone, if you don't know it, is like a big long stick of chocolate. So with systems that have like monolithic logs, monolithic topics, you need to have 3 replicas, right, for availability and redundancy. If you go down to 2, then you either have to give up redundancy or availability. So, with quorum-based systems that need a majority, you just lose availability. And with something like Kafka, where you can choose either, you have to go for one or the other. And so you just don't choose replication factor 2. But with Pulsar and BookKeeper, things are a bit different. So we already talked about ledgers, and a topic is just a series of ledgers. But actually, a ledger in itself is also broken down into fragments. So we can actually further subdivide our ledgers. And so in our first fragment, when we open the ledger, maybe we're just writing to bookie 1 and bookie 2, but bookie 1 becomes unavailable, maybe network partition, or it fails, or it's too slow to respond. So an ensemble change happens. So any uncommitted entries are then sent to the new bookie, to bookie 3, and writes continue and reads continue. As soon as bookie 1 is back, we have full redundancy. And if it doesn't come back, then auto recovery can kick in to move the data to another bookie. And it can just keep jumping and jumping. So if you ever see in your logs, if you're ever looking at your BookKeeper logs and you see stuff about ensemble changes, this is what it is. It basically means that if ever there's a problem with a bookie it can't write, it just changes the ensemble and carries on. So we get continued write and read availability with redundancy, even with the replication factor of 2. So this is just a quick example. This is sequencediagram.org. I highly recommend it for sequence diagrams. You can write some text and it will draw it out nicely for you. So this is as an example of Pulsar publishes a message, a client publishes a message to a broker. It sends that ad to 2 bookies. They both acknowledge the write, and then Pulsar acknowledges to a client. Then we get a second message, and the write to bookie 2 fails. So bookie 1 acknowledges, but the broker is now able to change the ensemble. And it can actually say, well, actually, now I'm going to change to bookie 3. So we've got now 2 fragments, one with bookie 1 and bookie 2, and a second fragment with bookie 1 and bookie 3, and things carry on, and we have not lost any write or read availability, and we still get redundancy. So there you have it. So if you want to look at the progress of our work on running without the journal, it's still work in progress. Still in most of it is actually written, and it's in our kind of private Splunk fork of BookKeeper. So we're in the process of trying to get that back into open source. So you can follow the discussion on GitHub. And we also have the TLA plus specifications for just the regular BookKeeper protocol, but also the one with the limbo status. So thank you. And if there's any questions.